So last week, like I said, we kind of introduced friction, but we didn't get into a lot of detail about it. So today it's kind of a little more detail about what friction is, the two different kinds of friction, okay? And we'll look at a few more problems involving friction. And then this week, hopefully near the end of the week, we'll start talking about Newton's third law, okay? And we'll talk about that kind of more after Easter. Okay, so there's two kinds of friction. There's kinetic friction and there's static friction. Static friction means that the two surfaces are not sliding past one another. Okay, so there's no there's no sliding. So if you have like a car's tires and they're not spinning, that's static friction. Okay, if they are spinning, then they're sliding past the surface that they're on, and that would be kinetic friction. All right, something sliding down a hill, that would be kinetic friction. Something set on a hill that's not sliding would be static because it's not moving. Okay, so if I have like a book with something on it, for example, like let's say I take this book and I put my calculator on it. Okay, obviously right now there's like basically no friction because there's nothing going on. But if I start inclining the book, okay, at some point the calculator is going to slide down the book, right? Okay, but right now it's still dealing with, there's some static friction here. The steeper, there's a fair amount of static friction. Agreed? Okay, it's not going to get, wow, that's really sticky. There we go. Okay, we finally got some kinetic friction there as it started to slide. Okay, now the amount of friction is determined by a couple of things. Okay, and we talked about this. This is what we talked about last week. Is that the force of friction is determined by mu, which is how sticky the two surfaces are when they're in contact with each other, and normal force, which describes how hard the two surfaces are being pressed into one another. All right, those two things can increase or decrease the force of friction, both static or kinetic. They affect them the same. Okay. All right, so like I said, we have static friction if there's no movement going on. Okay, so if I'm looking at this example here, okay, I've got this applied force, okay, of 165 newtons that's directed 30 degrees below the horizontal. Okay, the desk remains stationary. We want to calculate the force of static friction acting on the desk. All right, if the desk doesn't move, what's the net force? 0. All right, so that means that the force of friction back on the desk and this component of the applied force are equal. Okay, they have to be, otherwise the desk would be sliding. All right, so friction is resisting backwards. Okay, so that would be this force, and this would be the horizontal component of our applied force. They have to be equal because the desk's not moving. Right? So static friction questions are actually often quite a bit easier than kinetic friction questions because there's really only friction and whatever force is going forwards, and that's it because the object's not moving. In a static friction question, the net force is always 0 because the object's not moving. Okay, whereas in a kinetic friction question, the object is moving, there could be an acceleration, or maybe there's maybe it's a constant velocity, whatever, okay, but there's more stuff to do generally when the object's in motion. All right, can I calculate this force? Yeah, I know the angle, 30 degrees, and I know that this force here is 165 newtons. Right, so I can very easily calculate, okay, what the horizontal component of that would be. Right, I just have to go cos of 30 times the hypotenuse, 165 newtons, and I'll have my horizontal component, which, as we said, is going to be equal to the force of friction because the desk isn't actually moving. So, whoop, not cos of 3, cos of 30. All right, so we got 143 newtons. Actually, yeah, we have 3 significant figures there. So 143 newtons is our force of friction, but it'll be negative. Okay, because that horizontal component would be positive, be forwards. Okay, everybody all right with that? Yeah? Okay. I want you to calculate the acceleration of this 10 kilogram block. Actually, sorry, no. Let me say that again. The block is not accelerating, so it's 0. There you go. You're welcome. The block is just sitting on this incline. Calculate the force of friction. That is 20 degrees, yeah. Okay, so I got a 20-degree incline. The mass is just sitting on it. It's not sliding. Okay, calculate the force of friction. So if it's not moving, the forces down the ramp and the forces up the ramp are equal. Okay, what force is pulling down the ramp? F parallel, right. Okay, not gravity. Gravity's pulling straight down. I know we keep wanting to say gravity, but okay, gravity pulls this way. And we're going to need that if we're going to calculate F parallel. Now, relationship between F parallel and the force of friction we just said is that they are equal but in opposite directions. So the force of gravity here will be 98.1 newtons because it's a 10-kilogram box. Okay, this side here is the normal force, but I won't need that to answer this question. Okay, and this side is F parallel. And then this angle here is the same as the angle of incline. So if I want to calculate F parallel, same as I always do on an inclined plane, I find the opposite side, so the sine of 20 degrees times 98.1 newtons. Okay, so all right, so we got 33.55 newtons. I only have two significant figures here, so we'll say 34 newtons. Okay, and then that means that FF is going to be 34 newtons up the ramp. Okay, next step in this question. What is the coefficient of friction between the 10-kilogram box and the plane? So you're looking for mu. Okay, see if you can figure out how to calculate mu. Okay, remember that this is the friction formula, right? Mu times the normal force. So if I want to calculate mu, I already have the force of friction. All I need is the normal force, which is the adjacent side of that internal triangle we always draw. And this is what we're going to be leading up to, is eventually, okay, an inclined plane question might say you have this box on an inclined plane, the coefficient of friction is this, and then you'll have to calculate the force of friction as part of solving that problem. Okay, so for right now, we want to calculate the normal force, okay, which will be the cos of 20 degrees, since it's the adjacent side, times 98.1, and that'll give us, okay, Fn, and then we can calculate the coefficient of friction. All right, so it's 92.18, and then now that we have that, okay, we can divide our force of friction, which we calculated to be 33.55. So just so we have everything there divided by our answer. All right, so our coefficient of friction is 0.36. We only have two significant figures, so 0.36, right? Coefficient of friction is usually a decimal. It's usually less than 1. No units on the coefficient of friction, right? Okay, and the reason we talked about that last week, but the reason for that is when you manipulate for mu, you're dividing the force of friction by normal force, so the newtons cancel and you're left with a number with no units. Okay. All right. So this is what I was talking about a minute ago. Now we're talking about a kinetic friction type of situation. Okay, so I have an inclined plane with a coefficient of friction of 0.125. Okay, there's a 120 Newton force pushing or pulling the box up the ramp. We want to calculate the acceleration of the box. So just like any other inclined plane question, except now we've thrown in that we have to calculate the force of friction. It's not given to us. All right, so I'm going to give you guys a couple minutes on that one. Okay, so the first thing we got to do is identify the forces that are going to be important in solving this problem. Okay, obviously friction is going to be one of the forces, and which way is it going to act? Right, the opposite way of which way it's going. So we're going to assume that's going to be this way. Okay, so force of friction will be here, and what else will be down the ramp? F parallel, right? Okay, we don't know how big those are just yet, but they're both down the ramp. So we've got our usual triangle inside, normal force on this side, force of gravity over here, F parallel here, okay, and this 25-degree angle. So we've got FG being 196.2 newtons, okay, 20 times 9.81. So if we want to find F parallel, okay, we're going to go sine of 25 times 196.2. Okay, so F parallel is going to be 82.918. Newtons, and then I got to calculate the force of friction. So if I want the force of friction, I need mu and I need the normal force. Okay, so I've got to calculate normal force using cos. It's the adjacent side, so Fn will be the cos of 25 times 196.2. All right, so we got a normal force of 177.817. I'm going to multiply that by the coefficient of friction, which was 0.125. All right, so our force of friction is 22.227. Newtons. Okay, so now I know the force is down the ramp and I know the force is up the ramp. Obviously, there's more force up the ramp. There's only about 105 newtons worth of force down, 120 up. Okay, everybody follow me there. All right, so if I want to calculate the acceleration, I need net force and mass. I have mass, but I don't have net force yet. Net force is the vector sum of all forces. So that'll be 120 plus negative 82.918 plus negative 22.227. All right, so 120 minus 82.918 minus 22.27. All right, so I've got a net force of 14.855 newtons up the ramp. Divide that by 20, and I've got my acceleration. All right, so my acceleration is 0.74 meters per second squared up the ramp. Okay, so it's a bit more involved, okay, but there's nothing in that, like there's no one step that's overly difficult. It's just remembering which steps you have to do or figuring out which steps you need to do. Okay, that makes sense to everybody there. All right, we already did this one. Okay, we did it with the other example there where the object didn't move. Okay, so we'll just skip over that one. And we'll skip over that one too. Okay, now kinetic friction. Okay, direction of kinetic friction in any case is always opposite the direction the object is going. Okay, in the case of static friction, the direction of static friction is always opposite the direction the object's being pushed. Okay, even though it's not moving, it's just whatever is opposite the direction of the other forces. Okay, but for kinetic friction, it's always opposite the direction of movement. So that's all we have to remember there. Okay, so if we're accelerating down an incline, then the force of friction is up the ramp. Okay, if we're accelerating down the incline, or sorry, up the incline, then force of friction is down the ramp. Okay, right, we're gonna skip over that, and we've done one. We just did one like that, so we'll skip that one too. All right, we just did one like that, so we're gonna skip that one too. Okay, I thought I had something else on there. I do. Okay, to give you some idea here, guys, of the coefficients of friction for kind of common things. Okay, well, common, we say common, I don't know how often you see copper against copper, but anyway. Okay, you can see here that in almost every case, the coefficient of static friction is greater, okay, than the coefficient of kinetic friction. Right, and that's why we were saying static friction is always greater, right, than kinetic friction, and that's why we don't want to spin our tires. Okay, that's especially if it's on ice. That's not going to help us to move forwards. We want to use static friction, so we want to. That's what basically all traction control modes are trying to do is keep your wheels from spinning, so you have more efficient friction. Okay, things like that. So we got like a rubber tire on dry asphalt. This one of the ones that's greater than 1. Okay, so it has a coefficient of friction of 1.2. Okay, but look, it drops significantly if those tires are spinning. Right, so the coefficient of kinetic friction is considerably lower. The amount of kinetic friction is lower. Okay, rubber tire on wet asphalt, half. As soon as that asphalt is wet, okay, the traction decreases by a half. Right. Rubber tire on dry concrete. Okay, so asphalt's a little bit better than concrete. When we're looking at like wet concrete, okay, it doesn't decrease quite as much, but still decreases a bit. Okay, look at ice though. Okay, I mean, yeah, you're probably looking at that and going, Coder, you said like makes a huge difference. It's like 1/1000th. But we're talking about practically no friction at all here. Okay, so we want to harness every last bit of it if we can. Okay, so obviously this is something we deal with all the time. Okay, and it's something that we have to be aware of. The amount of friction between rubber tires and ice is very, very low. Okay, that's why we go to all the lengths we do in Canada to make the roads safer, right? We throw sand on them, we throw salt on them, okay, all that stuff to help get them melted off. Okay, curling stone on ice, okay, also pretty low. Okay, they're made of rock. Teflon on Teflon, pretty low. Okay, and then if you've done any cross-country skiing, okay, you'd use different kinds of wax. Different kinds of wax have different coefficients of friction. Okay, and then this one here, synovial fluid in your joints. Okay, you guys are young, so you still have some of that. When you get old, you have less and less cartilage in between. Okay, this is the stuff that keeps your joints lubricated so that they don't click and lock and grab like old men like mine do. Okay, so that stuff is pretty slippery. Okay, has a coefficient of friction of 0.01. Okay, and it's the same static or kinetic. Okay, so take care of that stuff. You don't want to have to keep getting artificial stuff injected into your knees all the time. Big needle, side of the knee. Yeah, it's lots of fun. Wait, you don't want to go there. All right. And we've looked at that. So, okay, I want you guys to go back to the vector quantity sheet and the inclined plane sheet. Just go back and forth between those. Okay, kind of one of each, and then we'll see which ones give us trouble, because that always kind of tells me what areas I need to focus a little bit more on that worksheet. So let's keep working on that. I'll put it back up here on the board in a minute. Okay, but let's work on that, and then we'll figure out what areas we need to work on, because obviously tomorrow's Tuesday, and there'll be a quiz on Newton's second law, one that probably will involve a friction question as well. Okay, so we need to be ready for that. Yes. Okay, so number 6 is a vector addition question, really. Okay, I've got 2 kids that are making a snowball and they're putting it into position to make this snowman. Okay, so one child pushes with a force of 130 newtons. So I'm going to start out by drawing my free body diagram here. Okay, the snowball is 50 kilograms, so it's big. Okay, we're pushing 130 newtons at 15 degrees west of north. So here's due north, and this would be like 15 degrees west of that, so 130 newtons. And then the other kid is pushing due west with 110 newtons. All right, so there's my free body diagram. In the end, this snowball is rolling somewhere in between those 2 forces. Okay, well, the way to figure that out is to draw a vector diagram of that. So I'm going to start out with the 130 Newton force. Okay, so this will be our y, and this will be our x. And then we have our 110 Newton force going due west. So the snowball is going to be pushed, whoa, that's a very crooked line, but you get the idea, okay, in this direction here. So we have some unknown angle. This will be our net force. This will be its y and x component. All right, so same as always. So if I want to find black x, okay, black x will be the sine of 15, because it's the opposite side, times 130 newtons. And black y will be the cos of 15 degrees times 130 newtons. Okay, so 33.646. newtons, and that is west. Okay, and then cos of 15 times 130. Okay, so 125.57 newtons, and that'll be north. Okay, for the green line, I only have a west one. I only have an x component. Okay, so now to calculate blue x, okay, I'm just going to add the two x's together. So blue x will be 110 plus 33.646 because they were both west, so 143.646. And blue y is 125.57, okay, because it's the only one. Okay, now that I have those, I can do Pythagorean theorem to get my net force. Okay, so my net force is 190.794 newtons. Okay, and I need its direction, so I'll find that. Okay, using tan, so it'll be y over x, so 125.5703. All right, so I've got an angle of 41.16. degrees, and for me that's north of west. Now I've got the net force and I've got its direction, but the question wants the acceleration, so the acceleration will just be the net force divided by the mass, which was 50 kilograms. Okay, so when we do that, we should get 3.82 meters per second squared at I have 41.16 north of west, but that would be the complementary angle, so 41.12 or 48.8 degrees, depending on which direction you went. Okay, making sense? All right. Sometimes it comes down to that, and I have very often put a question like that on the unit exam, okay, where it's a net force question, but it's also a vector addition question. So we have to make sure we're still okay with our finding x's and y's and stuff. Awesome. Yeah, they're generally different, the same skeleton, but yeah, slightly different context to the questions. Yeah. That way I have consistent assessment, right? All right. Any others? Okay, keep going then. More come up, we'll go over them.